Hey everyone, welcome to this explainer. I've got to say, as a guy who is completely obsessed with figuring out exactly how the universe ticks, this specific topic is easily one of my absolute favorites. Today, we are mastering a fundamental truth of chemistry. The macroscopic properties we can see and touch in our everyday world are completely dictated by microscopic structures and interactions that we literally cannot see. We're going to conquer 8 specific constructed response questions by breaking down these concepts. Okay, let's dive right into this.
Here is our roadmap for today. We'll be hitting extreme states of matter, carbon and living systems, diamond and graphite structures, the science of dissolving, crystallization and temperature changes, and we'll wrap the whole thing up with an exam-ready quick revision. Let's get started.
Section 1. Extreme states of matter. Moving way beyond just your standard liquid and gas.
So we usually just think of matter as solid, liquid, or gas, right? But pushing temperatures and pressures to their absolute extremes changes everything. Our first question asks, what exactly does a supercritical state look like? Take a look at this progression, from liquid to gas to a supercritical fluid. It's wild, because right at that critical point, something amazing happens. The distinct boundary between the liquid and gas phases just completely vanishes. The particles get highly mobile, and the substance suddenly possesses characteristics of both a liquid and a gas at the exact same time. So whatever you do on the exam, don't just call it a very hot gas. The memory hook you need here is above critical temperature and pressure, no distinct liquid-gas boundary.
All right, let's jump to another extreme state and see how this builds our understanding of ionized gases. The question here is, in what way is plasma created in a fluorescent tube?
Okay, picture the inside of that everyday fluorescent tube. It's filled with low-pressure gas. The second you flip the switch and apply electrical energy, energetic electrons take off. They accelerate rapidly and violently smash into the neutral gas atoms. I mean, these high-speed collisions are so intense, they literally knock other electrons right out of their atomic orbits. This leaves you with positive ions and free electrons. That chaotic resulting mixture of charged particles, that is what we call plasma, and it's what eventually produces the light. So your memory hook is simply ionized gas containing free electrons and ions. Moving right along to Section 2, Carbon and Living Systems, the building blocks of life.
Transitioning away from extreme states, let's pivot over to carbon. Here's a question that trips up a lot of students. Most of the molecules we study in biochemistry are organic in nature. So where exactly does the difference exist between the organic and biochemistry branches of chemistry? It's a really great question, because the apparent overlap between these two fields causes a ton of confusion.
Let's clear this up. On the left side, organic chemistry is all about the element carbon itself. It zeroes in on the structures, the properties, the reactions, and the synthesis of carbon-containing compounds. We're talking things like hydrocarbons, alcohols, and polymers. Now look at the right side. Biochemistry is organized entirely around living systems. It focuses on the chemical substances inside living organisms, like proteins and DNA, and all those metabolic processes happening right inside living cells. So while biochemistry absolutely looks at carbon-based molecules, it only cares about them in the context of biological life. Your memory hook, organic focuses on carbon, biochemistry focuses on living systems.
Section 3. Diamond and graphite structures, a tale of two carbons.
It is crazy how wildly different carbon's physical forms can be just based on atomic arrangement. Our next question bridges atomic structure directly with optics. Give the reason for the brilliance shown by diamond, and can you improve it?
Just notice the path of light entering the diamond here. Diamonds have a remarkably high refractive index. This means when light hits it, it hits the brakes. It slows down and bends, undergoing significant refraction. And because of the diamond's internal structure, that light gets trapped, experiencing repeated total internal reflection. It just bounces all around inside before finally shooting back out. That is the brilliance. And to answer the second part of the question, yeah, absolutely, humans can improve it. By expertly optimizing the cut angles and facet proportions during polishing, a jeweler makes sure that maximum light is reflected straight back toward the observer, rather than just leaking out the sides. Now, on the flip side of carbon, we have graphite. The question asks, why is graphite slippery to touch, and which property of graphite enables it to be used as a lubricant?
This head-to-head matchup perfectly nails our golden rule. Structure dictates function. Over on the left, graphite basically consists of carbon atoms arranged in flat hexagonal layers.
Now, while the covalent bonds within those specific layers are super strong, the attractions between the layers are incredibly weak. This allows the layers to just slide right over one another with minimal friction, which is exactly why it feels slippery and functions perfectly as a lubricant. Contrast that with the right side. Diamond's rigid, three-dimensional interlocking network structure gives it extreme hardness, making it ideal for heavy-duty cutting tools. Same exact element, totally different behavior.
All right, section 4, the science of dissolving, breaking the lattice. Let's bring this back to your kitchen for a second. What actually happens on a microscopic level when we mix salt into water? The prompt is, explain the dissolution of sodium chloride in water.
Okay, so sodium chloride starts out as an ionic crystal lattice, basically a tightly packed grid of positive sodium ions and negative chloride ions. But then the polar water molecules attack. Water is polar, meaning its oxygen end has a partial negative charge and its hydrogen end has a partial positive charge. The negative oxygen ends aggressively gang up on the positive sodium ions, while the positive hydrogen ends swarm the negative chloride ions. The water totally surrounds the ions, weakening their lattice attractions. The hydrated ions are then pulled apart and just sort of float away. And remember this crucial point for sure. This is a physical process of dispersion. You are not creating a brand new chemical compound here.
Section 5. Crystallization and temperature changes. Heat and solubility.
So if that's how things dissolve, how do we get them to undissolve? The prompt asks, why do different compounds have different solubilities in water at a particular temperature? It's essentially a molecular tug-of-war. Everything comes down to a precise balance of three forces. First, solute-solute attractions, how tightly the compound holds on to itself. Second, solvent-solvent attractions, how strongly the water molecules cling to each other. And third, the solute-solvent attractions, how well the water and the compound actually interact with each other. The fundamental rule here is that for something to dissolve, the favorable interactions between the solute and solvent absolutely must be strong enough to compensate for the disrupted interactions of the solute and solvent being torn apart in the first place. This is the real molecular mechanics behind that old saying, like dissolves like.
Let's apply this to a real practical lab scenario for our final conceptual question. Why can NaCl not be crystallized from water just like KNO3?
Take a look at these solubility graphs where temperature is on the bottom axis. Potassium nitrate, or KNO3 on the left, has an incredibly steep curve. Its solubility changes vastly with temperature. If you have a hot, saturated solution of KNO3 and you cool it down, its capacity to stay dissolved just drops off a cliff. Boom, you get massive, dramatic crystallization. But look at sodium chloride on the right side. Its curve is relatively flat. Its solubility changes only slightly over that same temperature drop. Heating the water barely increases how much salt can dissolve, which means simply cooling it down is highly ineffective for getting crystals. If you want salt crystals, you have to use evaporation.
Finally, Section 6, Exam-Ready Quick Revision. Let's master this test. All right, let's lock in these memory hooks so you are totally prepared. Supercritical state, above critical temp and pressure with no distinct boundary. Plasma, ionized gas with free electrons and ions. Organic versus biochem, carbon compounds versus the chemistry of actual living systems. Diamond's brilliance, that's high refractive index and total internal reflection. NaCl dissolving, polar water hydrates and physically separates the ions. Solubilities, it's a delicate balance of solute and solvent interactions. NaCl versus KNO3 crystallization. KNO3's solubility swings wildly with temp, NaCl barely moves. And finally, graphite. Weak forces between layers let them slide right past each other. You guys now have the conceptual blueprint of the physical world. So, next time you sprinkle salt on your dinner, flip a light switch, or even just jot something down with a pencil, I want you to ask yourself, what are the invisible atoms doing right now to make this exact reality possible? Thanks for hanging out with me for this explainer. Keep questioning everything.
Like, subscribe, and join us for more amazing videos!